Hi, Algebra 1. I wanted to run through the homework that I asked you to try on page 101, 102. So they want us to predict the next couple terms. So I got 4, -20, 100, -500. So it looks like we are multiplying by -5 each time. So then that's going to give me 2,500 and then like -7,500. So this is geometric because I'm multiplying. Number 2, I have 3, 5, 8, 12. So I add 2, I add 3, I add 4, well, I'd add 5, add 6, add 7. So being that these are not consistently adding, this is neither arithmetic or geometric. Number 3, 64, 48, 36, 27. So let's see. It looks like I'm subtracting. What's 64 minus 48? I can't do it in my head. So that's going to be a 6. So I'm going to subtract 16 each time. And then that one's not, that's like subtracting 12. And then that's subtracting, what is that? 9? It looks like the perfect squares, but I'm subtracting perfect squares. So that'd be -4. And then that would be -2. So that's not subtracting by a constant term either, so that's neither. Number 4, I got 1.5, 0.75, 0, -0.75. Looks like each one of these I'm subtracting by 0.75 each time. So we keep going through with that. So that's going to be -1.50, -2.25. So I'm subtracting 0.75 each time. So this is arithmetic because I'm subtracting. Number 5 at the top of page 101, I got 40, 10, 5/2, 5/8. So it looks like I'm dividing by 4, which is the same thing as multiply by 1/4. So that's just, it's going to give me 5/32. 4 times 32, that's 8, 128, 4 or 5/128. So because I'm multiplying, this is going to be geometric. Number 6, I got 1, 11, 1, 1, 1, 1, 1, 1, 1, and then 1, 1, 1, 1, 1, and 1, 1, 1, 1, 1, 1. So that's not adding or subtracting. That's just adding a 1 to the end, so that's neither. Number 7, -3.6, -5.4, -8.1, -12.15. And it looks like, let's see, what are we doing here? 3.6. Looks like I'm subtracting an extra 1.8 maybe, then 8.1 minus 5.4. That's subtracting 2.7, so that's not going to happen. I wouldn't even worry about the last term, so that's neither. Number 8, -64, -47, -30, -13. This looks like I'm, oh, that should have been a 13, sorry. So it looks like I'm adding 17 each time. So -13 plus 17. That'll be 4 and 21 if I keep adding 17. So that's arithmetic. Okay. Number 9, create predictable sequence that is not arithmetic or geometric. Don't let's not worry about number 9. That's just kind of a silly one. Number 10 says for every ton of paper recycled, 17 trees are saved. So you want to say if it's identify whether the following statement represents discrete or continuous. Okay, so every ton, so 1 ton, it's 2,000 pounds, 17 trees saved. Well, I would say it has to be continuous because you could have continue OUS. You could have a decimal amount of tons. Number 11, the hair on your head grows ½ inch per month. That would also be continuous because your hair doesn't just grow the ½ inch, it grows all the way through. On the backside, page 102 says the city of Buenos Aires adds 6,000 tons of trash to landfills every day. Okay, so that would also be continuous because you could do a portion of a ton. Number 13, in 1929, from Black Thursday, October 24th through Black Tuesday, October 29th, the Dow Jones average stock declined by 25%. Okay, so you have a decline of 25%. So it doesn't go right to 25%. It just, so that also have to be continuous. And a whole bunch of continuous ones. And then number 14, they want us to, it looks like, graph it. It says create a graph in the statement X, Y. Be sure to graph correctly. So it says approximately 3.24 billion gallons flow over Niagara Falls daily. Okay, so I guess you could do something like this. 0, 1, 2, 3, and we could count up by 3.24 billion. 4, 8, something like that. So you could have something like that. And it would be continuous because it's going to keep going. It's kind of a silly one. Number 15, the average person laughs 15 times per day. Okay, so what we could do is we had 0, 1, 2, 3, and then count by 15, 30, 45. So starts laughing, starts laughing, starts laughing, something like that. And that would be, so this would be discrete. The reason is you have a set amount of times to laugh. You can't laugh a portion of times. This would be continuous because is it 3.25 some days, 3.23 other days. So we have that. All right. So let's take a look where we should go. All right, let's take a look at page 105. This is lesson 2. It says, shh, please be discreet. Okay. All right, so the first one is one of those, which one doesn't belong? 5. So you have 2, you have -2, you have -½ you have the square root of 2, and you have 2.22 repeating. Okay, so you can make a claim that this one doesn't belong because it's a positive whole number. This one doesn't belong because it's a negative whole number. This one doesn't belong because it's a negative fraction. This one doesn't belong because it's a square root. This one doesn't really. So any of them could go there. All right, so let's take a look. Down below on page 105, it says open up the math lunch discuss. Okay. The Library of Congress is considered the largest library in the world. They often receive boxes of books to be added to their collections. Since books can be quite heavy, they aren't shipped in big boxes. On average, each box contains 8 books. Okay, so we have 8 books per box. On average, if on average each box contains 8 books, how many books are received in the library when you have 6 boxes, 10 boxes, or n boxes. Okay, so let's do our table. We're going to do B and F at B for books. So on day 0, you get 0. On day, and then it says on average 8. So on one day, there's 8 books in a box. Or if you have 2 boxes, there's going to be 16. On 3 boxes, there's going to be 24, and so on and so forth. Okay, so each time we're adding 8. So this got to be arithmetic. So our recursive has got to be next plus 8 or something like that. And our explicit equation, we're going to say F at B is equal to, we do have this 0 term here, which is great. So we can start, so we can say that our common difference of 8, so 8B plus 0. We can do that. And if we take a look at our graph, on day 0, we have 0, 0. On day 1, we have 8 books. So on and so forth. Actually, I don't want to connect those dots. Okay. I don't have enough to go any further. So it looks like we have everything there. Flip the page. Remember, if we talk about the domain is basically going to be, it didn't ask for the domain. Let's not worry about that one. All right, so next page 106, problem number 2, it says, many of the books in the Library of Congress are electronic. About 13 ebooks can be downloaded to a computer each hour. So 13 ebooks, those are electronic books rather than a hardcover book. Each hour, each 1 hour, okay? It says about 13 ebooks can be downloaded on the computer each hour. How many ebooks can be added in 3 hours, 5 hours, so on and so forth? Oh, actually, let's go back and answer this one. If we wanted to answer the question on the page before, if I had 6 books, I'm going to go 6 times 8, so that's 48 books. If I plug 10 in here, that would give me 80 books, or 8n is our equation. Forgot to answer that. All right, so on the ebooks, I'm sorry back there, I'm flipping around. All right, so I can do 13 ebooks in an hour. So if we'll do E and F at E. How's that sound for ebooks? So we start out with none. First hour, 13. Second hour, 26. Third hour, 39. So we're basically adding 13 to each one. You know what? If we go back on the last problem, this would have to definitely be discrete, because they're sending me 8 books a box. They're not sending me a partial box. On this one, it's going to be continuous, because I can, I'm loading the computer as we go along. So if we try and graph this, I get 0, 0, 113. So it's up there. So this one I would do a straight line because it's continuous. Okay, so our equation, because it's arithmetic, we're going to say F at E equals 13E, and then plus 0, because we have our 0 term. And then what I can do is, so that's my explicit. My recursive is going to be something like next plus 13. Number 3, the librarian's work to keep library orderly and put books back in their proper places after they have been used. A library can sort a shelf 3 books in a minute. So 3 books for every 1 minute. Okay. If the librarian can sort the shelf 3 books in a minute. How many books can the librarian take care of in 3 hours, 5 hours? Ooh, 3 hours, 5 hours, and N hours. All right, so we need to think about how we can convert this. So if I wanted to make this per hour, I have to realize there are 60 minutes in 1 hour. Okay, now the minutes cancel, and then that's going to say that I can do 180 books in 1 hour. Okay, this is called dimensional analysis. I'm just multiply those together. I cancel out the units. All right, so then we can go ahead and think about our equation. So our explicit would be, well, let's, if we made our table, books and F at B. So at 0, 0. At 1 hour, there's 180. At 2 hours, there's 360. I don't even want to try and graph this. I mean, it would just be a graph that's doing this, something like that. This would be continuous because, you know, they don't just do 180 books and then the next hour another 180 books. They're sorting as they go along. So our explicit, because we have 0 term, and we're adding by 180 each time. So we're going to go ahead and say that F at B is equal to 180B plus 0. Our recursive is next plus 180, something like that. And we said it's continuous. Okay, we're good. Number 4 said, would it make sense in any of these situations that there be a time when they have 32.5 books had been shipped? I'd say 32.5 books being shipped would not make sense as far as boxes go, because I'm not going to send a part of a book. But as far as the ebook goes, yes, you could do 32.5 books, because think of, you know, as it's loading to the computer, it's going to be loading a portion of the book. Think about the fill line on your computer as you're loading something, or on your phone. Number 5 says, which of these situations, 1 through 3, represents discrete, which represents continuous? Well, we just went back. Okay, number 3 was continuous. Number 2 was also continuous. And then number 1 would have been discrete. I guess we could also argue this one could be discrete because we can't do a portion of a book. There's a good argument for that, so I'm not quite sure which one we want to go. Okay, so flip over to the next page, page 107. It says a giant piece of paper is cut into 3 equal pieces, and then those 3 equal pieces. So you start out with a sheet, and then you cut it into 3 pieces, and then you cut those 3 pieces into 3 pieces. So you're going through that. So on this situation, we start out with 1 sheet of paper. So we'd call this P, and then we'd call this F of P for paper. So at 1, so this is at 0. At 1, I have 3. At 2, I have 9 folds or cuts. And then what's going to take place at 10, 20, and end cuts. So if we look at this, I'm multiplying by 3 each time. So if we're multiplying, this means it's geometric. So I'm going to start with this. I don't have to use an n minus 1 because I have a 0 there. So my recursive is going to be next times 3. My explicit is going to be F at P equals our first term 1 times our multiplier, and we're going to raise that to the P power. And then it says, what can we do if we had 10? Well, that's going to be 1, 3 to the 10th power, you definitely want a calculator for that. So if you go 3 raised to the 10th power, that's 59,049 pieces of paper you have. If you did it 20, you get 3 raised to the 20th power. Holy cow, that's a lot. 3 to the 20th power is 3, 4, 8, 6, 7, 8, 4, 4, 0, 1. That's a lot of cuts. Okay, so in n cuts, here's our n cuts basically. Just change the p to an n. So we have the equation. The domain of this function, remember we're looking at this top thing, is going to go from 0 to infinite cuts. Of course, we can't, it's going to get too thin. And then we could also say that, you know, x such that x is greater than or equal to 0, something like that. As far as the range goes, would it make sense to do 5.2 cuts? And not really. I mean, you could say you only cut a portion of a paper, but I mean, we're trying to cut this all the way down, so I don't think this would make sense. We're not going to cut a portion of a paper. We're going to cut the whole thing. And then would it make sense to look for the number of cuts it takes to make 53.6 cuts? And I'd say that's also no, because we're not going to only do a portion of a paper. So being that each individual cut is independent, I would say this has to be discrete. And then number 7 on page 108 says medicine taken by a patient breaks down in the patient's bloodstream and dissipates out of the patient's blood system. Suppose that 60 milligrams of anti-parasite medicine is given to a dog and the medicine breaks down. So 20% of the medicine becomes ineffective after an hour. Okay, so if you had started with 60 and it's going to decrease 20%, that means I would have had 80% left in the dog. Okay, so 80 plus 20 is 100. So I'm going to make this a decimal. We are decreasing, so I don't need to put a 1 in front of it. So this is geometric because we're multiplying. So basically, if we made our table, we'll go dog and F at D. So at 0, there's 60. And then at 1, we're multiplying by 80 each time. So that's then 48. So multiplying by 0.8. And then 48 times 0.8. That's going to be 38.4. So on and so forth. So you're just multiplying by 0.8. So it's geometric. So because I have this very first term, which is great, I'm going to say that F at D for my explicit equation is going to be the first term, 60, times 0.8 raised to the D power. And then my recursive is going to be next times 0.8. Identify the domain. The domain would go from, again, we're looking here, from 0 days to infinite days, or whenever the drug is gone out of the dog. Would it make sense to look for amount after 3.8 hours? And I'd say yes, because the drug is decreasing as we go from each of these, okay? So it'd be a continuous situation that would take place. Would it make sense to look for when there's 35 milligrams of medicine? Yes, 35 milligrams would make sense because we started with 60, so we're just decreasing from there. So we could definitely figure out where that would take place. And which of the function models, problems 6 and 7, are discrete or continuous? These are both continuous. Okay, and what needs to be considered when looking for a situation in the context and deciding if it's best to discrete or continuous. So if things are going to lessen each day, then that's kind of good to figure out. Okay, so for your homework, will you go back to page and do 103 and page 104? That was pages prior to our lesson. See how you do with that.
Okay.